Give me order and time, and I will give you design. Daniel Dennett elegantly summarizes in his quote the creative engine at work in Darwin's theory of evolution. The core process of design in human-involved disciplines implicates an extra factor, intentionality. In both, a process of production and reproduction takes place through the exchange of encoded information. While in biological systems such information is embedded and embodied, shape and organization are information, in human-based practices, the encoding requires an external, explicit and abstract notation system. We owe to Leon Battista Alberti's obsession for identical reproduction the concept of a notationally stable artifact, the original, the final version of a work. A set of codified abstract information, the sublimated sum total of intentional decision, ready for exact serial reproduction. A means becomes a goal, notation takes command, design divorces making, thus incidentally sanctioning also the figure of the author as the subject associated with it. Codification, the act of producing a notation artifact, implies a system of mediation, and all forms of mediation involve modes of storage, manipulation, and transmission. Friedrich Kittler points out that the mutual relations among these modes are critical in order to comprehend the entire system of mediation, also remarking that the computer is the first technology of mediation that automatically combines them into a single system. Differently from a sketch on paper, geometric data in a computer is truly three-dimensional, which can be generalized to n-dimensional, this is a crucial detail for the development of artificial intelligence. The possibility to build a relational architecture in the code means also that digital technology can process and manipulate information in such ways that difference and variation can become programmed design features of a unique process. For architecture, this shakes the foundation of mechanical standardization and, with the simultaneous possibility to inclusively mobilize materiality and machines, of the Albertian design-making authorial divide. Technology has always defined the operational boundaries of the design space, shaping the features of the realm of possibilities that it simultaneously opens. Its advancement pushed those boundaries and widened that space in a movement that is not one of endless improvement and substitution, but one of continuous restructuring, enabling paradigm shifts. For one, photography did not replace painting. Technology's outcomes enable also cultural changes. A brilliant example of this symbiotic relation is the invention of collapsible tin paint tubes for pigment conservation. This tiny invention, patented in 1841, allowed painters to finally work in plein air, when before that invention they were forced to stay in their studio, otherwise their pigment would fail and decay. This, as a matter of fact, enabled the painters to watch and observe nature, and in turn enabled the birth of Impressionism. Technology has also a bias, showing preferences that reinforce certain possibilities while obfuscating others, thus altering our worldview as we operate through its lens. The tools we make in turn reshape our mindset and our action. Think about the sentence, just Google it. Environment and technology also mutually reveal their shape from their reciprocal interaction, disclosing operational possibilities and boundaries. We cannot escape technology, and any way of improving our human condition is through it and not without. It is an inevitable source of both opportunities and problems, but the former will outweigh the latter only when coupled with apt theoretical paradigms and open-ended design approaches. What is advocated here is a speculative stance that does not thrive on narrative alone, but one that deals also with processes and dynamics through computation, nonlinearity, and complexity. But technological propagation and paradigm renovation progress at different paces, thereby causing a rift. Computation acts as a catalyzer that accelerates processes and exposes this rift. Computation itself can be defined as information processing. It tries to compress infinite quantities of data in finite sets of operations. It is a process that predates and transcends the modern digital computer and can operate on a variety of instantiations, whether based on a material or abstract system. The introduction of an explicit mathematical model, which requires layers of abstraction and a notation system, exposes the limit of computability as compressibility/reduction. Algorithms themselves emerged from material narrator practices. Modern computation gradually evolved from concrete towards the increasingly abstract forms. But purely descriptive or linear algorithms, such as those governing CAD systems, are not good enough to manage complexity. For instance, a linear algorithm for all the possible moves in a game of chess, is theoretically possible, but in order to build a calculator to account for all possibilities, the mass of the universe would not suffice, while biological systems elegantly attain similar complexity with only 4 elements, the nucleotides A, C, T, G. It is the von Neumann's model of a self-reproducing machine that was the key to overcome the purely descriptive model and open the way for emergence-capable systems, which develop in algorithmic paradigms like multi-agent systems, polyautomata, and so on. Computational methods are sought in the effort to tap into the complexity that Dennett alluded to, while retaining the ability to steer in order to meet specific goals. But we must come to terms with 2 important aspects of intentionality. First of all, it can be distributed, and machines have also their own bias or intentionality. By machine, here I refer to the concept of abstract machine, which is, in general, a finite sequence of operation. Sol Levitt is a key figure in this regard. In 1967, he wrote the sentence, "The idea becomes a machine that makes the art," a theoretical model for his wall drawing series, sequences of operation or algorithms to produce site-specific installations. Levitt is fascinated by the creative possibilities of a relentless machine and wants to question the figure of the author, the art piece, and the cut between the acting subject and the object of attention. The temporal dimension also enters the process through the concept of iteration. The decisional process disgregates and it is redistributed at a granular level. The myth-laden moment of conception is no more, as representation gives way to simulation. The process is as important as the object, because it captures the dynamics that generate the object itself as a result of interacting relation over time. Likewise, the true creative power of computation and design lies in its pervasive incorporation in the decisional process, from thinking to making, unfolding in time iteratively. And that can truly happen by giving into its way of thinking like an abstract machine. Computational design, then, is a matter of methodology rather than the adoption of a specific tool set. I should introduce, for the sake of clarity, the distinction that Matías del Campo makes between computational and computerized. The difference can be better explained in the comparison between Antoni Gaudí and Frank Gehry. Gaudí makes use of intellectual models, mobilizing material through mathematical and geometrical understanding as probes to navigate a design space for the generation of form, not only in the famous hanging catenary model of the Sagrada Familia, but also in the transition to the catenate surfaces and the Boolean construction of the rose windows. He thus relies on computational methods. Machines are an active part in his process of creation. Their inevitability is a means to resist easy figuration and immediate implementation, expanding beyond human limitation. Gehry, on the other hand, relegates computer to accessories for digital reproduction around a traditional human-centric understanding of intuition, talent, and sensibility. He still relies on the typical tropes of creation as the irreplaceable intuitive moment, whereas the computers are just accessories to rectify and rationalize. In a computational approach, The decisional process is distributed within the system at the metabolical level, producing a causality network with multiple possible branching at each step. An action can trigger multiple effects and consequences. Conversely, single effects can be the result of multiple causes. Authoriality metabolically binds itself to the decision that propagates at each iteration. In the words of John Fraser, the minute you start encoding things, you put intentionality into things. In simulations, one defines the rules of engagement for a system that unfolds over time. When employed for the study of a phenomenon, they act as a map to an existing territory. But when used in a speculative stance, the map precedes and engenders the territory itself. Once the simulation apparatus is built, it needs to be explored to see what sort of territory is engendered. Baudrillard refers to this reversal as precession of simulacra, and to the engendered territory as hyperreality. Computation itself is thus to be considered as a design medium, in the twofold meaning of means and territory. In computational design, computation is at the same time material, territory, and means for open-ended exploration. A simulation/machine/algorithm and their enactment are not one and the same thing, and they do not compute for themselves. The questions of intentionality, authoriality, and their implied politics, intended as distribution of power and resources, now translates as who computes. Algorithms are themselves not mere tools. They incorporate intentionality and distribute it across the process with their enactment, causing effects that can be experienced at the aesthetic level because the experience involves the totality of our interconnected senses. They are modes of thought in their own right, and their embedded logic becomes an aesthetic operation. In order to instrumentalize self-organization and emergence to harness higher forms of complexity, their generative engines must be coupled with a selection activity, a continuous exploration, refinement, and channeling by means of interacting with one or more decision-making personae. It is in this articulated and distributed web of decision, both encoded and as a result of assessment of the outcomes, that intentionality and also reality have moved. In the elegant words of Stephen Shaviro, what we need is an aesthetic of decisions in a frame of emergence and self-organization. The adoption of computation in the design process requires thus a constant activity, involving the exertion of a certain sensibility in order to gain fluency and the potential for expression. The concept of craft, the exercise and discipline of sensibility, the free flow of ideas through the hand of the artisan, according to Ruskin, can be applied to computation if emancipated from an exclusively human-centered perspective. Craft can be redefined as an accumulation of knowledge that sublimates into sensibility. It is then neither tied to the exclusive use of hands, although it is haptic, it requires a sensory and enactment apparatuses as one thinks by acting, and thus involves, again, aesthetics. Nor it is a unique human trait. Machines can also learn and refine their own kind of sensibility, they can develop their own kind of craft. This distribution of decision across the design process in the computational scenario leaves the question of authoriality as open as it was when Sol Levitt first raised it with his wall drawings, possibly even more. Even if someone writes an algorithm, the outcome generally exceeds the individual's capacity to conceive that, and thus the authoriality is at least partially shared. The rise, or better, the resurgence and pervasive diffusion of artificial intelligence with machines and systems capable of ever-increasing degrees of human and non-human intelligence and sensibility presses the matter even further, with radical possible landscapes of change in the design process. It is thus appropriate to speculate on the potential for novelty that AI might bring in shaping potential rising cultural changes, in the same way in which collapsible thin tubes enabled Impressionism. For instance, one interesting aspect of AI is the fact that it engenders a computational space or self-computing space as its training progresses. This dimension adds to the time dimension introduced by simulation and iteration. Another important aspect exposed by the attempts and difficulties on the road to fully automated driving is that labor is an inherently logical activity. Thought and action intertwine. The automation of human labor in its pervasive and granular distribution of interconnected microtasks transcends the modern age division of intellectual versus manual labor, with analog repercussions to the design-making divide. Any computational thinking machine capable of agency and decision can suddenly face the problem of percolation of simple decisions into ethical dilemmas, from steering a wheel left or right to the updated version of the trolley problem, where a car in a switch must quickly decide whether to go across a single person or a group of people. Meanwhile, what's not unseen is the trend of progressive expansion of machines, robots, and algorithms alike in what were considered exclusively human domains, including creativity. See, for instance, AlphaGo and the famous or infamous Move 37. This impending tide presses us humans to constantly rethink our species' identity and role in a larger ecological perspective. If a machine can do it, then it's not our defining exclusive trait. The processes of design should become more and more a conversation with ever-increasing intelligent entities and acknowledge the symbiotic nature of our relation with it and the fact that it exceeds our attempts to control it. Thank you.